So this is asking about electrophilic aromatic substitution. So we're thinking really about all of these things essentially being on benzene rings, and what are they going to do to a benzene ring? Because right in electrophilic aromatic substitution reactions, the benzene ring is the nucleophile. So things that add electrons into the ring will activate the ring. So a lot of these things have lone pairs. They're activators. So the first question is, which of these are activators that actually activate the ring? So basically the question is, does it have lone pairs? Or can it do hyperconjugation? So this is really a carboxylic acid. So also a hard part of this is, do you recognize things as they're drawn out? That's what this really is. So that's not an activator because it doesn't have a lone pair. That's actually a deactivator. Methyl is actually an activator, not a great activator, but it's an activator through hyperconjugation. Now bromine does have lone pairs. So the halogens, fluorine, chlorine, bromine, and iodine have lone pairs, but they're still halogens, right? They're all the way to the right of the periodic table. They're really electronegative. So actually, even though they have lone pairs, they're the one exception, they are not activators. There's two electronegative. But oxygen is not that far to the right in the periodic table. So in this one, the methyl and the oxygen are activators. Now the next question says, well, which one of these are withdrawing groups? So again, this is kind of just the opposite of the other one. But again, you need to draw a little bit of these structures out. So for this one, NO2, it's really important to draw these things out. Where that attaches ring, there's a nitrogen with a plus charge. So that's definitely a deactivator, a really good deactivator actually. So that is definitely withdrawing. NH2 is actually an activator, has a lone pair there, so that's not going to be a withdrawer. This is actually an ester, but the oxygen is attached to the ring and there's a lone pair there. So that's an activator actually. Not a great activator, but it could be an activator. And then finally, this SO3H, right, again, you got to be able to draw these things out. That's kind of the key. It's a two-part really thing. Can you draw these things out and understand their Lewis dot structures? So this one, the sulfur, is actually electron withdrawing because it's bonded to all these oxygens, so it makes this sulfur really delta plus, and a really good withdrawer, so a deactivator through resonance. And then the last one, now it's kind of adding these two things together. So now it's asking about which of these are orthopair directors. So again, we're thinking activators and only one type of deactivator, those halogens. So anything that's an activator, and then the halogens, even though they're deactivators, right? Like bromine, because they have lone pairs, they still direct orthopara. Carboxylic acid, again, we know that's a deactivator, so that's not it. CN, that's a carbon triple bonded to a nitrogen, so that's a really delta plus carbon. That's not an activator. Fluorine, or it's not an orthopair director. Fluorine, even though it's a deactivator, it is actually an orthopair director. OH is for sure lone pairs, and OCH3 is as well. So things that have lone pairs always direct orthopara. The lone pairs are next to the ring, but not all things that have lone pairs are actually activators. So the exception is the halogens: fluorine, chlorine, bromine, and iodine.